Okay, so good morning, everyone. I'm also talking about a far-out topic since my talk is about space and a new DAO that I've co-founded about space biosciences. And I don't know if anyone recognizes this picture on the front page. It's a small satellite. It's called BioSentinel. It's currently in orbit now, and I'll come back to that a bit later. But the aim of my talk is to kind of convince you that you should care about spaceflight and particularly the impact of that on biology. So if I haven't done that by the end, then we have to start the talk. Okay, so space biosciences, it's a study of the impacts of spaceflight on human health. Two of the main kind of factors we think about are the impacts of microgravity and also radiation. And the reason we want to study this is because if we can solve for some of the problems that we get in spaceflight, this will translate to new technologies on Earth, so in personalized medicine and various other technologies, which I'll come back to again. And the image on the right is supposed to represent DNA damage by a high energy particle. So we get a lot more double strand breaks in space. So the goal of SpaceBioDAO is to build up a global community, so bringing together stakeholders who are interested in this topic. And at the moment, we have groups, labs signed up from the States, from Europe, but we're always looking to expand, not just looking for researchers, but anyone who's interested in space biosciences. So yeah, if you are, please come and find me, and we can talk about that more. But the idea is to make space more accessible to everyone. And the kind of reason why we're doing it now is because we're in a new era of space discovery. So I'm using the European Space Agency's, the ESA's definition now that we're in space 4.0. So they count space 1.0 as when people first looked up and decided to study astronomy, astrology. Space 2 was when we had the first government journeys into space. And then space 3 is just gone. So this is the first kind of private commercial launches into space. And now we're at the point where, there's really a new landscape of space exploration, and we're starting to see private citizens go into space. And this is largely down to the kind of big investment from industrial players as well over the last decades. So we're now at the point where launch costs have decreased, so it becomes much more feasible to send humans into space, but also to run experiments in space. And the goal from NASA is to get the cost down. This is a plot showing the cost per weight by kilogram. So by 2040, they want the cost to be off the scale. So maybe $50 to send a kilo into space. So like I said, we're already in this new sort of era of space exploration. And when US citizens were surveyed a couple of years ago, 50% of them said that if money were no object, they would travel to space. And I was going to do a quick survey here to see how many of you think that you would travel to space. I don't know if you would just put your hand up. If money were no object. Right, so I was close because I predicted that 100% of the people here would be really up for that. But when you speak to people who actually have the money right now to buy a ticket, 20% of them say that they'll travel only after there's been 1 year of safe travel shown. And that goes up to about a third after a few years. But yeah, the point is we're going to see more and more humans in space. And according to key opinion leaders, by 2030, you'll probably know someone who's been to space, so you're going to know an astronaut. And we can also expect that to translate to medical breakthroughs on Earth. But one thing to remember is that humans have actually been living in space since the year 2000. So the ISS has been continuously occupied every day. Someone's been living there since then. But importantly, none of them have been there for more than about a year. And the ISS is in low Earth orbit, so it's relatively shielded compared to deep space. So it means that a lot of the kind of biological impacts we still don't know about. So that means that out of space exploration, humans are kind of the part that we know the least about, but that also means that there's the most opportunity to study this. And some of you might know of this study, the NASA twin study. So this was a huge effort where they sent two identical twins. One stayed on the ground, one was in space. They've both been astronauts for a long time. And they measured them using like a multi-omics approach, so trying to track, every kind of biomarker, every test there is. That's what they did. They compared them, and this was done using 10 research streams. So this is showing some of them there, and so 10 teams of researchers. And what that really showed us was that it's kind of a good way of doing science. So these 10 teams from different research institutes were all brought together, and they designed the experiments from the beginning with this collaboration in mind and sharing the data. And it also relied on a lot of coordination, but by working together like this in this manner, they could get the most impact from one set of experimental data. So I think this gives us a kind of blueprint for how we can start to do science a bit differently. So many of the kind of biological impacts of spaceflight have been known for a while, but there are still many that we don't know about, and we're still learning about them now. So some of the key kind of features are highlighted here. So telomere lengthening in space, DNA damage, oxidative stress. And I can just highlight a few of them rather than looking through all of that. Some of them are particularly interesting for us because they sort of relate to effects we might see in aging or inactivity. So that includes like bone density loss, muscle loss. So this happens when you're in space. And you also get aging of your arteries by effects that seem like decades. But there are still many areas of concern that we really don't know enough about. So our immune systems change in space. We see epigenetic changes, mitochondrial dysfunction, that could also have gone into aging. And also the kind of change in how fluid is distributed leads to sort of structural changes in your eyes and your brain. So there's a lot to learn about. And this kind of multi-omics way of studying people in space means that we're going to see new ways to kind of develop personalized and precision medicine. So these astronauts are being profiled individually to get like the correct countermeasures developed for them. And now there's more and more people going to space. So historically, people who've been into space are astronauts, and mostly, white, male. And now we're starting to see for the first time kind of bigger distribution of people going to space. So we're kind of naturally going to be in a better position to learn more about people more generally. So NASA has recognized that we need to understand more about what happens once we go out of low Earth orbit and further into deep space, which is going to be relevant if we ever want to have humans living on the moon or on Mars. So they sent just now the first deep space biology experiment on this satellite that I showed you at the start. So right now this is somewhere orbiting, and you can track it if you're interested. And what it has on it is this payload of yeast cells. They designed special microfluidic chips that allow them to store yeast in a kind of dried out form, and then they bring it back to life at various time points just by adding water. And the goal of their experiment is to study double strand breaks to look at radiation damage. So on the CubeSat, they also have a pixel detector, which allows them a medipix detector, which allows them to detect the presence of high impact particles, so they can measure that high energy particles. So this is a really nice setup. But there's a reason why they use yeast, because they're able to, it's brewer's yeast, they're able to just dry it out and bring it back to life. And actually, this is kind of related to the last talk, I guess. So right now we have the problem that we can't do the same if we want to send mammalian cells, human cells, or organelles into space. So this is one of the big challenges in the kind of experiments that we're going to be designing, is being able to advance that so that we can go to that level. And the other kind of side of things is that we need to translate experiments into a really kind of small miniaturized way with as much automation as possible. And the other kind of impact of that is going to be that as biology, we've heard the last days, we know it's becoming more about data, more and more data intensive projects. So the more that we want to run these kind of AI-powered experiments, the more relevant these kind of tools such as automation and miniaturization are going to become more useful. And the other kind of side of things, as I said, is that it's making sure that we use the same experiments in the most efficient way. So we're not wasting any data, we're getting everything out of it that we can. And that's going to also include sharing the data publicly. So our first project and our first goal from the community is, like I said, our overall goal is to democratize access to space, but we want to launch the first DSci space experiment. And the plan for this is to use a CubeSat, so the same one that NASA are using right now up in space. So these are the size of a shoebox, and they're originally designed as a like an educational tool, because they could be really reproduced and teams could work on them. But they're now just being adopted to run scientific experiments. So there are more and more launches every year. I think there were thousands last year of these small satellites. And they're a really good way to kind of make the experiments modular. So this is something that we're looking to do. So the real challenge now becomes, as a researcher with your experiment that you want to run in space, how on earth do you fit your whole lab, into a shoebox? So it involves many different areas. Some of them I touched upon before. But we have kind of three main groups or teams in the DAO. So the first of these is like biolab. So these are the ones designing the experiments. So we have probably 15 projects right now that are being considered for translation into a shoebox. And so they're involved with the kind of science, so the question that we're asking. And then we need the hardware lab. So these are people who have expertise in miniaturization, microfluidics. And they're the ones who have to tell the biolab whether or not their project could ever work. And finally, we have software lab engineers figuring out how we're actually going to analyze all of this. And all of these three groups need to work together to refine the overall experiment design. And in this way, the kind of workflow allows us to design the best experiment that we can. And it also means that, of all these groups that suggest their projects, whichever one ends up being voted in by the DAO, the rest of the researchers will still be involved in working on it. So we're still sticking with that blueprint of having multiple groups of researchers all working on the same mission. So I'm just showing a rough roadmap. This is the first time that we've presented SpaceBioDAO, so it's early, which is especially why, like I said, if you're interested at all, please come and find us. Kajan's also here in the audience. He's my co-founder, and he's also CEO of Space Biosciences. So yeah, say hi to either one of us if you're interested. So like I said, this is the first public presentation. We're still building our community, so please do have a look and join. And our goal is to get the first of our experiments finalized and launched. I'm saying Q1 2024 to be optimistic. And then what we really need to do is expand and get our kind of launch calendar done for the rest of the time. But the other thing is as well, we're obviously in quite a new area of exploration. So we need to remain quite agile in terms of what we're going to be looking at in a couple of years. So this is how our site looks at the moment. So we have a Discord. There's not much on it yet. But yeah, as I said, very happy to be here, speak to everyone, especially because I'm from the UK and London's the town that I live in. And yeah, that's all. Thanks for listening.
Any questions?
Yeah.
Anybody? Yes.
I have two quick questions, I guess. One is, I don't know much about biology in space, biology in space, but it seems that like the two main factors would be radiation and like lack of gravity.
Yeah, that's two of the big ones, yeah.
Yeah, and so that would sort of like, if it's true that they are the two main factors, I wonder how they are tackled as challenges. One could easily think of like, well, we could do radiation shielding and like do gravity somehow with mass, I guess, or like rings, or I don't know. So I'm wondering, is it part of the vision to tackle these big factors? And the second question is like, how open is this in the sense that like, if someone from outside wants to sort of become part of the project somehow, how does that happen?
Okay, I'll start with the second one first. Yeah, so the DAO is open to anyone. We have our core team. There's about 10 of us right now working on it, but not full time. So yeah, we're looking for more people to be involved. You don't need to be a researcher. You can just be interested in the area, and there are going to be millions of ways that you can contribute. And then in terms of the first question, which was around whether we will be specifically tackling the areas of microgravity and radiation, I think that our focus is going to be, we kind of have a core area where we know, right now we have 7 areas that are known to be affected by these factors. I think part of the problem is that we don't know how much of it is actually due to, for example, the radiation, as opposed to any of the other things like confinement or circadian rhythm disruption. There's still quite a lot of unknowns in the space. But like I said, the goal in the end is going to be, using these multi-omics approaches to look at really specialized therapies.
You had a Q3 launch of token. Are you just using that for governance and fundraising as an ERC20? Are you how is this tying into blockchain technologies, or is that just a vehicle for ordinance?
So it's going to be for governance, so for voting. So the idea is that, as I said, for our first project, we're going to have these set of experiments in the community, which includes the researchers, but also anyone who is interested to join. They'll vote on which of the projects to focus our resources on. But we're also a registered company, so that is going to be held by the DAO itself.
Okay. And then how are you going to combat 51% attacks if your governance is managed by tokens, so that, I don't know, Virgin doesn't just buy enough of your tokens that you do whatever the heck they want you to do experiments on, or random dude.
Yeah, this is one of the challenges that I think every DAO worries about, is how to make sure we have fair voting. We heard Vitalik speak yesterday about quadratic voting, for example. So at the moment, we have not defined exactly how we're going to vote on governance, and it's probably going to be one of our first proposals that we do, is to solidify that. So yeah, it's been interesting to hear what people think so far here. And yeah, it's something that we're still figuring out, I guess, which is why we have till Q3.
So there's been a few experiments that I know of sending the mammalian cells to space. So to what extent are you building on what's already been done in terms of the hardware and technologies? Or is that something you still to explore?
Yeah, I think that the thing we're trying to do is make them as automated as possible. So right now, a lot of the experiments that are done by astronauts, which is great because they're not scientifically trained usually, and they have to be able to do the experiments. So you're already kind of bringing in an element of, turnkey engineering. But yeah, the goal for now is to be able to make these completely automated and go to deep space. So it means that our samples need to be stable for a long time in some of these chips. So yeah, I think it's still really early in that area of research.
Yes.
I've been thinking about space governance. I'm just curious what your take on it is from the standpoint of existing politics, because it's tricky. You can't even agree on what point the space begins or ends to different jurisdictions within sort of space law. I'm just curious what your thoughts are on going to looking at actually in terms of just trying to get on the same page, and there's quite a potential, especially if you're doing bio stuff, the potential, like a bio, something being released that, from above, I'm just curious, yeah.
Yeah, I mean, space ethics is a really interesting area, and there was a big meeting a couple of months ago, I think, where people were trying to figure out these kind of questions. And I think one of the goals really is, I had our scientific working groups, but yeah, ideally we need a policy group as well to kind of figure out some of these strategies. And yeah, again, it's an area where we still don't know how it's going to look in a few years. But yeah, we'll get people who are involved in policy involved too.
Cool, thank you. Another clear answer, yeah. Anybody else? Is it only since 2000 that people live in space? Wasn't it a bit earlier? Or?
I think that's the time that the ISS has been continuously occupied. But yeah, people were in space a bit before that.
Cool. Yeah, I mean, we can wrap up, take a break if there are no more questions.
Thank you.